Today we'll see about conservation of energy. Don't forget to like, share and subscribe to my YouTube channel. When you're just rubbing your hand, kinetic energy is converted to heat energy. Energy cannot be created nor destroyed. Total energy in the system is always remains constant. Don't forget that there are two types of systems when you are just talking about conservation of energy: conservative and non-conservative systems. When you say non-conservative, it is just dissipated forces are just exist. The law of conservation of energy states that energy cannot be created or destroyed. It can be changed from one form to another form and from one place to another place, but the total energy is remained constant. Or the total energy of an isolated system is a constant. You can see here the following. Let's see here. You have a spring here, a string here, and you are just hanging here a certain mass. This is supports, hang, stand, and hanging material. You see, when this just oscillates freely, like this one, it can have that there is a conversion of energy. You see here, here is just potential energy, here is potential energy, is kinetic energy. In between, you can get both types of energies, which means you can get both potential and kinetic energy in between of them. Which means the amount of potential energy here and the amount of kinetic energy, they have the same values of energy. If it is 10 joule, this is also 10 joule and this is 10 joule. If the system is just conserved, which means all other dissipated forces are just neglected. Or, you see, here is potential energy is 0, but kinetic energy is the maximum one. As you go here, potential energy is maximum, kinetic energy is 0 here. Here also potential energy is maximum, kinetic energy is 0 here. You see here, now here is potential energy, no kinetic energy here. The maximum potential energy is just observed here, kinetic energy is 0 here. Here's the maximum potential energy is observed here, no kinetic energy is here. Moves freely here, potential, potential. Here kinetic, potential, kinetic, potential. But the total energy remains constant, which means the mechanical energy of the system is potential energy plus kinetic energy. So in all cases, there is a heat energy exists in between. If we are just talking about dissipative forces due to air resistance, there is some amount of energy is just converted to heat energy and sound energy. See? Now let's take example here. Which one of the following is an example of dissipative force? Now you can see here that when you say dissipative force it is a non-conservative force, which means when you are talking about that, the change in kinetic energy plus the change in potential energy is equal to 0. If this condition should be holds true for conservative system. When change in kinetic energy plus change in potential energy plus the work done by friction under the absolute value 0, this is non-conservative. Non-conservative. You lose some amount of energy as a result of frictional force. Here in our case, when the pendulum is just oscillating freely, there is a dissipative force. That dissipative force is the drag of air. So gravitational force, electrostatic force, magnetic force, and what is known as the spring force. All these are just examples of conservative forces, whereas air drag or viscosity is just an example of non-conservative force. So our answer is just gone to B. It's just an example of a dissipative force. Another example. Which one of the following is not correct about conservative forces? Work done against conservative force can't be easily recovered. Work done by conservative force, not recovered. Work done against conservative force is path dependent. Work done against conservative force is path dependent. Now you see here, in the case of conservative, it is path independent. Conservative is path independent. But what is known as non-conservative force is path dependent. Now you can see here, the work done, the work they do can be recast as something called potential energy. The work they can do can be recast as something called potential energy. No. In conservative force field, mechanical energy is conserved. Yes, true. This is true. And this is also true. And you can see here, work done against conservative forces path independent. True. And in the case of what is conservative force, this is just not recovered. This is false. So the answer is A is just our answer here for this question. A pendulum bob of mass 100 gram stretched to a string attached to a string is released from position of 20 centimeter. What is the velocity of the mass as it passes through the equilibrium position? Now here you can have that the potential energy is converted to kinetic energy. Or you can write here that the change in potential energy is plus change in kinetic energy is equal to 0, which means the potential energy final minus the potential energy initial plus kinetic energy final minus kinetic energy initial, this is just equals to 0. Now, from a position of 20 centimeters, this is potential energy final is 0 because the final as it passes through the equilibrium position, the potential energy is 0 because h is equal to 0. And here in the case of initially, the velocity initial is 0. So kinetic energy initial is 0. So you can have that kinetic energy final minus potential energy initial is equal to 0. Which means kinetic energy final is equal to potential energy initial. What does it mean? Half mv squared is equal to mgh. Now, how much is the value of V as it passes through the equilibrium position? V is equal to the root of 2gh, which is just equivalent to 2 times 10 times the height is 0.2. This is in meter per second, which is just 10 to, this is 2 meters per second is the velocity as it passes through the equilibrium position. So the answer is just gone to D. A spring has a constant of 14 Newton per meter and a mass of 100 grams attached to it. When the mass attached to the spring is pulled 10 centimeters and released, what is the maximum speed of the mass? Applying the same rules and regularities, the potential energy final, this is elastic potential energy minus potential energy elastic initial. This is plus kinetic energy final minus kinetic energy initial. This is equals to 0. Now you can see here that this is just the spring. Now with this, there is where K is in the case of this one is K equals to 14 Newton per meter. And here the mass is 0.1 kilogram, 100 grams, and it is pulled 10 centimeters, means 0.1 meter. What is the maximum speed of the mass? Now it leaves. Now, as it comes to compress this one, how much is the velocity? Which means half of mv squared, this much amount. How much half of kx squared is the elastic potential energy. This is just equivalent. The two, the elastic potential energy elastic is equal to kinetic energy of the mass. Then this implies that half is just cancelled here. Then what is V is just the root of kx squared over m. Then V is equal to K is 40 times x is 0.1 squared over the mass is 0.1. This is in meter per second, which is just equivalent to, this is one of this is just cancelled, and 40 times this one is root of 4 meter per second. This is 2 meter per second. So the answer is just 2 meter per second is the answer for this question. From what vertical height does a 4 kilogram object is dropped in order to have a mechanical energy of 400 joule at a vertical height of 5 meters above the ground? Now you can hear is that here mechanical energy is potential energy plus kinetic energy. We have this expression from the law of conservation of energy. The mechanical energy is 400 joule. Potential energy is mgh, the mass is 4 kilogram, times g is 10 meter per second squared, and vertical height of this one 5 meter. This is the kinetic energy. Then kinetic energy is equal to, this is just the same as 200 joule. This is 400 joule minus 200 joule is equal to 200 joule. Then this 200 joule is equal to kinetic energy is half of mv squared. This is equal to V is equal to 2 times 200 joule over the mass is 4 kilogram. This is just the same as 100 by 4. This is 1, this is 100. This is 10 meter per second. Then you can have that V squared minus V naught squared is equal to 2AS, or this is 2AH. So this is just equivalent to H is equal to V squared minus V naught squared over 2G, which is equals to 10 squared minus 0 squared over 2 times 10. Then H is equal to 100, 2 times 10, this is 5 meters. So totally this is just, let's call this H prime. This is H prime. So the total H is 5 meters plus 5 meters. Or you can take here, this is just, let's take this is H, and this total H is just this one. So H double prime is from a height of 10 meters, the board is just allowed to drop. Now you can see this question again here. Consider the pendulum shown in the figure below. You can see it just oscillating A, B, C, D up to E. The pendulum bob was displaced first to a height of 20 centimeters and reached at point E and released from rest. What is the speed of the bob as it passes through a point which is 8 centimeters above the point C? Now you can see here that change in potential energy plus change in kinetic energy is equal to 0. This is just the same as M times G. This is the potential energy, 0.08 meter minus 0.2 meter plus the kinetic energy is half mv squared minus 0. This is just equals to 0. Here you can have that the mass is just cancelled here. G times this minus this one is minus 0.12. This is in meter plus v squared over 2. This is equals to 0. So this is just 10 and this is just minus 1.2 meter squared per second squared, because G is just 10 meter per second squared. This is just equivalent to plus half of v squared is equal to 0. Then half v squared is equal to 1.2 meter squared per second squared. As it goes here, it becomes minus. Then this is just v squared is equal to 2.4 meter squared per second squared. Then v is equal to the square root of 2.4, and this is in meter per second. This is the velocity at a point 8 centimeter above point C. Please don't forget to like, share and subscribe my YouTube channel. Thank you for watching.